Hello and welcome. My name is Elena Kozlikin and I'm going to give you an introduction into kinetic field theory. Kinetic field theory is a new analytical approach for cosmic large-scale structure formation. Actually, this is an introduction for 3 talks that all deal with different aspects of cosmic structure formation in the framework of kinetic field theory. So after this introduction, you can either go on to watch Sara Konrad's talk on the universality of the cold dark matter power spectrum, or you can continue with Carsten Littek's talk, who's going to speak about how to compute velocity power spectra and the kinetic linear Seldowich effect from kinetic field theory, or you can continue with my talk, which deals with a comparison of kinetic field theory and the standard Eulerian perturbation theory. Right. So what is actually the motivation behind this new approach? So first of all, we want to understand nonlinear structure formation, so how nonlinear structures form and evolve. We need this understanding in order to make reliable predictions for the matter power spectrum or higher order spectra, in order to interpret, for instance, re-cleansing observational data and to infer information about the nature of dark matter and dark energy from them. So another very important question is about the universality that cosmic structures exhibit. So one example are dark matter halos, where in simulations as well as in observations, you find a universal density profile. So one particular density profile that is found on galaxy scales and for dark matter halos around huge galaxy clusters. So the question is, where does this come from? So the question that we address with kinetic field theory is, how can we describe the evolution of these tiny density fluctuations in the cosmic microwave background in the early universe to today's really nonlinear pronounced structures that we call the cosmic web. So how do we do this? So our approach is particle-based. We go into phase space and we have the phase-based distribution of particle positions and momenta. We sample this by point particles and we propagate these particles in their respective trajectories in phase space. And only after this propagation do we actually compute averaged quantities like density power spectra, velocity power spectra, and so on. And the advantages of kinetic field theory are, first of all, it's particle-based, and second of all, it works in phase space, so that the particle trajectories in phase space actually cannot cross, and so by construction, you do not have a shell crossing problems that other analytical approaches suffer from. Right, so let's look in detail at the approach itself. So we're dealing with a non-equilibrium statistics of n classical initially correlated particles. And the main object of our theory is a generating functional, which you may know from quantum field theory. So it's simply a phase-space integral over the initial particle momenta and positions, which in our case is of a Gaussian form and can be actually fully characterized by the power spectrum of the cosmic microwave background, which is well known. And the dynamics is of the ensemble, of the particle ensemble, is encoded in this phase factor, where you have a auxiliary field J, which I will come back to in a minute, and these solutions to the equations of motion of particles. These can be split into an inertial motion, so basically free streaming, and the deviations of particle trajectories due to interactions with other particles. So let's see how these particle dynamics actually look like. So since we're dealing with classical particles that interact gravitationally, we have this nice Hamiltonian here. This describes just the free motion, plus here you have the potential part where the potential is just given by the usual Poisson equation. And since you have Hamiltonian equations. You can solve them by simply using a Green's function, because they're linear differential equations, and you can write down the solution to the equations of motion in this way, where you have the free part, so I indicates the initial particle positions and momentum, and here you have the propagator, which in the most simple case is just t minus some t initial. And then you have this part, which describes the deviation of particle trajectories from the inertial motion. And you have this force here, which indicates that the particles are actually interacting with each other. So as you may imagine, you cannot simply solve the equations of motion for an interacting n-body system. So you will have to somehow approximate this part, so the interaction part of the equations of motion. A clever choice of the, an addition. So since we're dealing with an ensemble of n particles, we have this shorthand notation where we just bundle the trajectories of all particles into the tensorial x bar, where again we have the inertial motion and the interactions here with the force F, which is just a notation. So as I said, you will have to somehow approximate the interactions later on. So a clever choice of the propagators of the inertial motion is to already include some part of the interaction. And this can be done by using so-called Zeldovich trajectories, where you choose your free propagator, inertial motion, and to reproduce the linear growth. And this you do by using a transformation of the time coordinates to the linear growth factor, for instance. And then, of course, you need to account that you've used part of the interactions in your inertial motion by adding this term to the usual gradient of the gravitational potential, which just tells you that you need to change the force relative to your inertial motion. Right. So now that you have your generating functional, you can compute density correlation functions from it. And the way to do it is you need to construct a density operator, and then you can apply to the generating functional and get endpoint correlation functions. Our density operator is actually a number density operator because we're dealing with discrete particles. And so it's just the sum over this Dirac delta function, which gives you a peak every time you encounter a particle. And this can be Fourier transformed. And then you just need to replace the particle positions by functional derivatives with respect to this auxiliary field that actually couples to the respective particle positions, right? So when you have this density operator, you can simply apply to the generating functional, in the end set the auxiliary field, because it's already physical, to 0, and then you get your power spectrum. So just an analogy to what you do in quantum field theory. So as I said, you need somehow to approximate the interactions between particles. So we have two ways to do that. One is perturbative, where you pull out the interactions in this operator S, and then you have to Taylor expand this exponential in order to apply this operator to the free generating functional, which just includes the free motion of particles, or the inertial motion of particles. Then again, you can simply apply your density operators that we have just constructed, and you get the density fluctuation power spectrum like this. Another way is to ask basically every particle about the average force it feels from all the different particles. So basically, we put ourselves in the position of each particle, we compute the average force. In a homogeneous and isotropic universe, this net force is 0. But we weigh the force that each particle experiences from another particle by the respective correlation function, so that we do get a net force. And this net force can then be evaluated, and we can just put it in this interaction term that can be multiplied to the free So the power spectrum that you could get was just the free or inertial motion, and this gives you a closed expression. So now I'm going to show a result that you get with this mean field approach. So here you can see, so this would be in black the linear power spectrum that you get. In red you get the KT result, and in blue we have the halo fit result, numerically calibrated from B. 2015. And as you see, with a kinetic field theory, you get results that are accurate up to, let's say, 10% to a K of about 4 or 5, which is really, really good for a purely analytical approach that needs no calibrations from numerical simulations whatsoever. So this is the introductions, and if you have to take something away from this introduction, these are the 3 following points. So kinetic field theory is a fully analytical, particle-based approach for particle structure formation. It doesn't have the shell crossing problem because we operate in phase space all the time where particle trajectories just cannot cross, and it yields comparable results to those obtained with numerical simulations, but in a fraction of the time because we just have to solve integrals instead of partial differential equations. So thank you for your time, and if you like, you can now continue with the 3 talks that I mentioned at the beginning of my talk. Thank you.